Hey guys, today we're gonna inverse design a photonic wavelength domain demultiplexer. So what is inverse design? We can think of it as generative AI that does electromagnetic design for you. So instead of designing things by hand, we can just give the AI our specification and it will automatically design the photonic integrated circuit for you. So let's get started. First, let's head over to our Luminescent AI GitHub repo. And once you are there, the link is in the description, and you can scroll down to our inverse design examples. Here we have the wavelength domain multiplexer. We click on that, and it will take us to a Google Colab notebook. So obviously, this is something that you can run on your local Linux machine as well. So first, we will run the install script in the first cell. So the script can be obtained by simply filling out our new user form at Google Forms. And you can see the link right here. So once we run the installation script, we can dive into our Python script. So imports, we're gonna import Luminescent AI frontend and also GDS Factory. So GDS Factory is an open source software that's backed by Google, and it allows you to do integrated circuit patterns in Python. And our software, Luminescent AI, works pretty nicely with GDS Factory. First, we define our path variable, which is a simulation folder that's created locally where all the design and simulation results get dumped into. Next, we specify the length and width of our design region. And this design region is pictured in red here, and you can think of it as a blank canvas that the generative AI can work its magic into. So this design region will get automatically modified by the AI to produce the desired design. So now the units here in this example are in microns, but you can use whatever units you like in Luminescent AI as long as they're consistent. Because in the end, we're just going to normalize, the backend automatically normalizes everything with respect to the center wavelength. Next, we specify our waveguide width. We specify our margins here. Then we create our GDS factory component by starting off with the design area in red. So we provide this convenience function called lumi that MIMO, multiple in, multiple out cell, and it just creates a GDS factory rectangle basically with with ports on different sides as you specify, and also with some with some initial geometry. So here I have length width west equals 1 means we're placing one port on the west side, and on the east side I actually pass in an array, and this is an array of the locations of the port centers along east side. So there's one here and one here. So input is one port, output is two ports. Input, we're passing in a signal of different wavelengths, and on the outputs we want to separate the signals according to their wavelength, which in this example is 1.2 and 1.8 microns. Okay. We add a little bit of margin between the source and port 1. That just helps with accuracy a little bit. Okay, so there we have it. So once we set out this geometry, we will proceed to define the layers in the vertical direction, and that's called a layer stack in semiconductor fabrication. So here we're actually doing a 2.5D simulation where we have the fields EX, EY, and HZ along a plane. And this is an approximation. And Luminescent AI is fully capable of doing 3D simulations and inverse design as well. But inverse design is something that takes up a lot of RAM. So for the sake of demonstration, we're gonna do this just in 2.5D to save on RAM and also to serve as a feasibility study, right? If the design converges in 2.5D, then there's a good chance that it will converge in 3D as well. So it's just a super quick feasibility study to see if our generative AI is capable of doing this. So the layer stack we define here is basically your standard silicon insulator stack. So there's this core material made out of silicon, and also this placeholder design material that we invoke, and this basically serves to mark out where the design area is. Next, we specify our targets in terms of S params. We have a bandwidth of 50 nanometers, so we want this to work for around 50 nanometers around the peak specified wavelengths. And to be honest, your signal is probably gonna have like less than a few nanometers of bandwidth. But we specify a wider bandwidth because there may be variability in manufacturing that's gonna shift your performance like a few nanometers this way or that way. You may have an unstable diode laser that's that adds another tens of nanometers of shift. So by building in this bandwidth requirement, you kind of I say build in some tolerance to different sources of variability that may arise both during fabrication and also during operation. Next, we define our wavelength groups. So we're working with 1.2 microns and 1.8 microns, and obviously they differ by a lot. So the difference in waveguide mode is also appreciable. So by putting each in its own wavelength group, we basically force Luminescent AI to solve a different waveguide mode for each signal, so that way it's more accurate. We define the weight because the final loss function is a weighted sum of the different losses with respect to each target. So targets is um, just an array of lumi.target, and here uh, the first one I specify um, a t param of of t21. So this O2 at 0 comes from if you worked with MEEP before, we copied their notation. So this just means optical port 2 at mode 0. So we want the signal to go from port 1, which is our source, to port 2 if the wavelength is in the first wavelength group, which is centered around 1.2 microns, right? And then the second target is I want the signal to go from 1 to 3 if the wavelength is 1.8 microns, plus or minus half the bandwidth. Yeah, so targets is just an array of targets, so that's pretty easy. Then I pass everything into our bake prop function. So I have path, component, wavelengths. I specify targets. This element parameter is for the sake of manufacturability, and it defines approximately the minimum feature size that's going to be present in the inverse design. Now, realistically, this can be low as 0.1 because you can easily edge a 0.1 micron feature on an SOI node. But here I make it a little bigger because if you specify a bigger feature size, it actually makes your design have wider features, which are nicer and more tolerant to manufacturing variations. Specify my field in void materials, init holes. So basically, I'm gonna punch holes in the initial geometry, and this is just something that helps with optimization. Stop loss. This is just a feasibility study in 2D, so I set it at pretty high level, 0.1, so it's gonna stop when the relative error decreases to 10%. Iterations, yeah, self-explanatory. Unrest. This controls the resolution, and it's normalized with respect to the wavelength. So we actually have adaptive meshing, even in inverse design. So that means we have more grid points in areas of silicon where the wavelength is smaller. Again, this is a feasibility study in 2.5D. And then Z is the Z coordinate to slice in our 2.5D problem. I specify some mode margins, materials layer stack, save that, blah, blah, blah. Okay, so I finally run this by invoking solve, which does the actual optimization. So as you can see here, it displays some problem statistics, and it goes through the different iterations, right? So this example actually runs fine on your laptop, and this was done with just 2 free CPU cores on free Google Colab. So yeah, so yeah, so it can, yeah, so it's not that computationally intensive. However, when you go on to do this in 3D, it's gonna take up like 10 times the RAM, and that requires just maybe like a server machine. Yeah, but this feasibility study is perfectly okay on your laptop. In each iteration, I can see the time. I can see how the design is doing with respect to our different targets. So here are the four T parameter targets around the different wavelengths. Ideally, they should be 1.0 in our case, but at the beginning, I'm getting much less than that, right? From the initial geometry. So as we go through the optimization, you can see the targeting improve. Yeah, so this is pretty quick. It only takes like 20 iterations to reach a 10% target, and this thing stops automatically. So everything is saved to your simulation folder, including this video that we generated. And you can dig up that video yourself, or you can play it using MediaPi. And here, as you can see, we have our final design here. Sorry if it looks a little bit scrappy. I think it's just the so the plotting I think makes it look a little bit rough on the edges. But if you just look at it, you can see that the feature size, the different the different wedges and holes are 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 not that small, right? It's probably around zero point 0.2 microns as we specified. And if we look at the field, so here we send in a Gaussian pulse, which is automatically synthesized for you, containing 1.2 and 1.8 micron signals. And you can see that the longer wavelength goes to port 3, while the shorter wavelength, now wait for it to repeat, and you can see the shorter wavelength going to port 2, just exactly as we specified. Now, you do see a fair amount of radiative loss as this signal scatters throughout the device. One reason is that we set the stop optimization threshold at 10%. So 10% of the energy is going to the wrong places, and you can see some of it getting radiated as loss here. But a lot of the radiated loss is actually due to the fact that our Gaussian pulse contains a lot of contains some energy at wavelengths that we don't care about. That's outside our optimization targets. Um, and those wavelengths are of course free to radiate anywhere. So yes, so in general, if you push in a Gaussian pulse, the fields are gonna look lossier than what they really are. Yeah, so there you have it. As you can see, it's this is super simple, right? I mean, it's just a few years ago, this will take up like an entire PhD thesis to be able to do this kind of generative AI for for electromagnetic design. But here, at Luminescent AI, we've simplified it so much that probably like even a high schooler can do this, right? You just put in a few lines of Python code, and there you have it. Yeah, so if this sparked some interest, please shoot us a note or ask any questions in the discussion sections. So this is for photonic integrated circuits. We also have inverse design examples for 3D printed antennas, metasurfaces, RF microstrip circuits. So all sorts of fun things that you can deal with Maxwell's equations. Okay, well, I hope this helped. Please subscribe and stay tuned. Ciao.